So today's speaker is Danny Weyns. He is a professor from Catholic University in Belgium. He's renowned for his work in self-adaptive systems, and that's what he's going to talk about today. I'd like to point out for people that are joining in, this is conducted as a webinar. So what we will have is that we'll have Danny give his presentation. You can ask questions through the Q&A at the bottom of the webinar. You should be able to see that. You should be able to enable. You should be able to click on an icon that says Q&A, and you should be able to post your questions there. Although you can also post your questions in the chat, and what I'll do is I'll moderate the questions at the end. If you put your questions in the Q&A, the other attendees are able to vote for your question. So the question that gets more votes will get priority in being asked and so on. And so we can have a discussion that way. And so without further ado, I'd like to ask Danny to go ahead and get started and tell us about self-adaptive systems, why, what, and how to engineer them.
Okay, thank you, Sam, for the introduction.
You can see your presentation, it's all good.
So let me start then with the why part. Why self-adaptation? I use this IoT application that we built at the campus in Leuven. You see here a set of modes that are collecting data in the environment, and they send that to a gateway, a central facility where people can collect the data and then take action when needed. Now the data is sent in a multi-hop fashion. That means that the modes get time fractions that when they can send their data from one to the other. Now, of course, it's a wireless network, and you see here how the signal to noise ratio of one of the connecting nodes is fluctuating over time. And this, of course, the changing interference causes a threat that the data will not reach the next mode. So what we can do is we can increase the power of the mode to send that data. Now these modes are battery powered, and this of course will drain the energy. An alternative could be that we said, okay, we don't send the data between mode 12 and mode 3 via the regular way, but we take a detour via mode 7. Now on the other hand, other modes in the network are also sending data. And as you can see here, the traffic in the network is not something that is stable. It's fluctuating as well over time. So this may then lead to having mode number 7 there in the middle being overflowed with modes and then, with messages. And that of course will also give loss of messages. So the question now for these for the engineer, the operator, let's say, is how to configure the network, in particular the power setting and the routes that messages take in the network, such that the system is of high quality, meaning that the messages are not getting lost or not too many, and the data is transmitted on time, meaning that data is not staying too long in queues, and that the energy of the modes is used carefully. Now the problem is, if you look at the number of configurations in this system, that's a really huge space. So there are many possible ways to configure the system. And the problem is, if you pick one of these configurations and you look at it over time, the properties of that particular configuration in terms of packet loss or latency or energy consumption, that is fluctuating all the time, exactly due to these uncertainties, the difference in signal noise ratio, the traffic that fluctuates, and so on. So for the operator, it's a very hard problem to figure out what configuration to use to ensure that the properties that you want in terms of the qualities are achieved. Now, if we generalize this problem to water systems, then you see the systems are often complex. The conditions under which they operate are uncertain. These systems often have to operate 24/7. You cannot shut them down to do anything. And if we don't take into account the uncertainties, the system qualities may degrade, as we have seen, or even worse, the system might just fail. Now, to do that manually, that is obviously not the most interesting approach because people are costly, they can make errors, they can probably not react at the moment instantly when the problem happens, and so on. So the general problem then is how to engineer software systems such that they achieve their quality goals in a trustworthy manner, despite of the uncertainties that the system faces. So giving, I hope, a bit of a motivation why we need self-adaptation, let me now zoom into what is self-adaptation. Now, self-adaptation is not meant to be the holy grail for these problems. Self-adaptation is just one, although probably prominent approach to deal with uncertainty and what I call here business continuity, meaning that systems need to deal with the uncertainty but cannot get down or taken down to change them. And in fact, the basic idea of self-adaptation is rather simple. You miss certain information at development time, so you collect that data during runtime, and you use that data then to resolve the uncertainties that you were not able to anticipate during design or deployment time. And when you know the uncertainties, you resolve them, you can reason about them, you can look at your goals and then adapt the system such that it realizes the goals. So the idea is simple, but the realization is actually not so simple. Let me continue with explaining a bit more in depth what we mean with self-adaptation and self-adaptive systems in particular. We have two principles. The first principle is called the external principle, meaning that a self-adaptive system is a system that can deal with uncertainty in a kind of autonomous way. So we don't want to have humans interfere more than necessary. Does not mean we don't want them, we just only want them with a minimum interference. For instance, they can say, what are my high-level goals? Or they might be involved in terms of certain decision-making when it is necessary. But the external principle takes, in fact, the black box position. You look at a system and it can handle something autonomously with respect to uncertainties. Then we also have, obviously, an internal principle, and then we look into that black box. And we see that the system then conceptually consists of two parts. The first part is in fact a regular system that interacts with an environment and that deals with what we call domain concerns. So basically what you want to do in the domain as a software system, the functionality you want to realize. And the second part then, that does not interact with the environment, but it interacts with the first part. And that part deals with what we call adaptation concerns. And adaptation concerns are concerns about the domain concerns. Let me clarify that in a conceptual model. Here you see a very high level representation of what a software system can look like. So a software system acts in some environment. So it takes input and it affects the environment. And what we distinguish the environment from the system has basically to do with the level of control. What you cannot control is considered the environment. Users and hardware and the like. Now, if the input has uncertainties, if you don't know from the system up front that things might happen, you might need an operator that monitors the system and might change things in the system whenever it is necessary due to these uncertainties. Now, if you change the software system to a self-adaptive software system, you see the change is very small. The operator is replaced basically, and the operator now only gives a set of high-level objectives to the system, and now the system is dealing with the change that is needed to deal with the uncertainty itself. So this basically represents the first principle. Let us now look into the system internally, and you see here the black box now open. The first part is a software system. Now what we do is we instrument that software system, allowing to observe the behavior and the structure of that software system and enabling to change its structure or change parameters of the software system. We also instrument the environment with probes, and that allows the second part of the system, the so-called managing system, both to monitor the system and to monitor the context in which the system operates, and then to adapt that system, that underlying software system. So basically, this represents a second principle. The system consists internally of two parts: a managed system that is controllable, that deals with domain concerns or domain goals, And on top of that, a managing system that deals with adaptation goals. Now, if you look in the world, self-adaptation is not something exotic or so. You see it everywhere. You see it, for instance, as I showed you, in the IoT network for data, for the routing in networks. You see it for auto scaling in the cloud, for instance, for server management, even for database management. So self-adaptation is actually there in the practice. But as you can see here, it is all these examples from companies are actually mostly focusing at resources, not so much at the application software, but more at the supporting services or the resources used for software systems. So what the rest of this talk, the main part, in fact, will be about how to engineer self-adaptive systems. So we want to understand what are the underlying principles to build and maintain and evolve such systems. Now the rest of this talk and the engineering part is structured in what I have called waves, in total 7 waves. And these 7 waves, they focus on different engineering aspects of self-adaptation. So different angles to the problem of how to engineer systems. So it's not about different approaches, but different angles to the engineering problem. Now the first wave is called automating tasks. And I will usually use a first slide for each wave as this slide here. On the top, you see the timeline. This whole field basically took off around 1998. I mean, it was already going on years before, but you have to start somewhere. And these were the first seminal papers arised at that time that really used the terminology self-adaptation, autonomic computer, and the like. In fact, there was 2 strands. On the one hand, engineers in practice, in particular, IBM was very active at that time, and still today in this field. And on the other hand, there were researchers, both in the US and in Europe, that were start thinking about this idea of self-adaptation. So the main driver initially was the problem that people faced in practice with the internet that arose and was really penetrating the business. There was a problem in terms of management of systems. The systems became integrated, more and more complex, and human operators got it a very hard task to manage such kind of systems. So the whole idea was then to look, how can we automate this, somehow replace parts of the humans to do that in an automatic way. And the ultimate aim was, of course, to let systems manage themselves based on some high-level objectives. Sorry. So an important milestone, in fact, in the field was this reference model that was proposed by IBM. They called at that time the entity that was dealing with adaptation, the autonomic manager, which I have shown you in that conceptual model, calling the managing system, which is a more common general terminology that we use nowadays. And you see that autonomic manager is deployed on top of what is called a managed element here. So it's the managed element that in fact needs to be tracked and needs to be adapted, which was usually done. The green box here, the autonomic part manager, used to be a human, and now we want to replace it by software. Let us look quickly into this green box and look a bit at the different functions that you see there noted. So the first part is the knowledge which is shared among all the other parts. And basically that knowledge keeps the representation of the underlying system, probably also its context and the goals that need to be achieved. And then the monitor, it collects data at runtime that is in fact fed to this knowledge to keep an up-to-date image of what is going on in the world with respect to that managed system. The analyzer then, it just looks at the knowledge and then it analyzes the knowledge and checks whether any adaptation is needed, meaning that the goals might be threatened or violated. And then it analyzes what are the options to change the system. Now, if adaptation is needed, the planner will then determine a plan, meaning what are the actions that I need to take to bring that system to a better state so that the goals are again restored or not violated. And finally, the execute element enacts then that plan. That means it will adapt the managed system element according to the steps that are described by the plan. Now, this leads, in fact, to a number of essential maintenance tasks that can be automated by self-adaptation or through self-adaptation. I take a bit of time to explain you these tasks because I think it's essential to understand what is really self-adaptation all about. So I start with the obvious one is self-optimization. Self-optimization, a system that self-optimizes, it optimizes its resource usages. So it ensures that the quality goals are achieved, but in a most optimal way. Now you see here an excerpt of our IoT network. And you see between mode 12, for instance, and mode 7, there is an arrow that states that there is with two numbers, 11 and 80. And these 11, that is the power of the mode used to transmit messages to 7. And 80 is what we call the distribution, is the percentage of messages that mode 12 sends direction to the gateway to mode 7. You see the complement, the 20 other percent is sent by 12 to mode 3. For that, mode 12 uses a power setting of 30. Now in the current configuration, you see, this is an example, of course, the packet loss is 9%, which is lower than the threshold of 10. That's okay. The latency is 4% of the total cycle time that all modes need to send to transmit their messages. That is smaller than 5%, so that is also okay. And the energy consumption is 24 coulomb, which is a given number that we require to transmit. Now we might allow the system to reason about possible alternatives using some technique that allows you to represent the network and reason about it. And for instance, if we would change the distribution of messages to 60% between 12 and 7, and 40% to 12 and 3, and we change also the power setting for the last part to 11, that configuration would allow, which gives us a packet loss, an expected packet loss, in fact, of 9%, similar as the previous, the current configuration. The latency would be improved, and also the energy consumption would be improved. So this would be a better configuration. We might look at other configurations where the packet loss is further improved, latency is less good, so this time above the threshold. This is a very good energy consumption, but we violate one requirement. We might look at another yet another alternative. And at the end, we might look at a set of alternatives and then look, is there any opportunity to switch from the current configuration to an alternative such that the goals are achieved and energy consumption is minimized. And actually, if we switch to alternative 3 in this simple toy example, that would be a better option. So the system will do that, and that way it will self-optimize. A second essential maintenance task is self-healing, where a system has the ability to detect and recover from faults. So that means it should achieve its goal, or in case of faults, it might be required to degrade gracefully. So back to our system, imagine that in this initial configuration, mode 9 fails. That's of course a problem because all the data that's sent by 9 is lost. This is of course unavoidable if the mode is gone. But moreover, all the data that mode 5 sends to 9 will not reach the gateway. And the data that mode 10 and all the parents of mode 10 reach will also not reach the gateway. So we need to take action. Now to take action here, what we might do is we might look at possible configurations or reconfigurations. And to determine which configuration to pick, we use what is called expected utility. And here you see examples of expected utility on the left hand. You see that if we achieve with a configuration a packet loss below 5%, we say the utility for that particular property is very high, maximum 1. If the packet loss is between 5 and 10%, the utility is considered 5. And anything above 10 is considered utility, giving me a utility of 0. And we give packet loss a weight of 0.5 in the total. The same for latency and energy, and you see then the expected utility, we sum up, in fact, the product of the actual utility with the weight for each of these properties. So let's apply this to one possible configuration. Let's use mode 5, sending directly to gateway all the data, which means it needs a very high power setting, 15, and it sent 100% of his data to the gateway. The numbers between these curly brackets are in fact the number that the mode gets in the time synchronization. So first the mode with number 1 will be allowed to send, then mode with number 2, and so on. So this mode 5 will be allowed to send to the gateway's data in the 14th step of the total cycle time of one cycle that all modes can communicate. Now, if we look at this particular setting, we might predict that the packet loss here will be 8, the latency will be 4% of the cycle time, and energy consumption 19. And if we compute then the expected utility, it will give us a number of 0.5. An alternative configuration could be this, where we send the data from mode 5 to mode 6. We need less power because maybe the mode is closer and we don't need to set the power so high. And here again, we can compute the expected utility, and you see the expected utility for this configuration is 0.13. Now in this case, if these are the only two options we would consider, we would take the first one because it gives us the highest utility. Let's look at the third one, essential maintenance task, that's self-protection. So how to defend against attacks. Consider this type of setting and assume it's a static setting. Now an attacker might start looking at the data transmissions and see, aha, there is a particular pattern. These modes, they send in a particular order the data, and based on that kind of information, attackers can really derive a lot of information about the network. And they might also use it, for instance, to transmit messages, unwanted messages, just around the time that particular modes are allowed to communicate and disturb the whole communication. So what we might do is, we might, as soon as we detect such kind of traffic based on normal traffic, and we compare it with what is going on, we might switch to an alternative schedule and change the order in which modes can send data. Or even better, what we might do is we might use alternative schedules all the time, switching, of course, not all the time, but regularly we might proactively switch to alternative schedules to disturb, in fact, or destroy the insights of the attacker. Finally, the last essential maintenance task is self-configuration, which allows the system to automatically integrate new elements. Imagine you have this setting, and now a new mode 16 arrives. So this mode, it might send discovery messages that the gateway then might reach. And the gateway might then look at, okay, what is the most optimal way to incorporate that mode? For instance, it might send a part of the data to mode 4, a part of the mode data to mode 9, and then we might establish a particular time schedule to send data to the gateway. And that way, the system has incorporated mode autonomously without any human involvement. So the insights of the first wave are that the automation of tasks is really one of the keys, if not the key driver for self-adaptation. MAPE-K, as we have seen, this monitor, analyze, plan, and execute reference model is a foundational model for self-adaptation. We have seen here 4 types of maintenance tasks, but over time many others emerged, but still today these 4 are considered as a kind of basic maintenance tasks, but many other so-called self-start properties have been identified later. Let us now look at wave 2, so-called architecture-based adaptation. Now the wave 2 emerged around 2004, and it went on for about 8 years. I mean, when I show these red bars here, it's not like exact, it's the main focus. So the driver for this wave was how do we engineer these systems? Because the ideas that were presented in the first wave were like a kind of fuzzy, but we needed, of course, engineering methods to engineer these systems. And then the perspective of architecture was crucial in this view. And in fact, this wave has 2 phases, if you want. On the one hand, architecture as driver to define self-adaptive systems. On the other side, architecture as a means to reason about adaptation. So let me first look at defining. This 3-layer model is in fact a model derived from robotics, was proposed by Kramer and McGee, I think it was in 2007 at the FOSE, as a kind of foundational model to define the key concerns and how to manage them and structure them in the engineering of self-adaptive systems. So basically the bottom layer is component control, is basically the managed system. So it accomplishes the functionality of the application. And you see here Darwin notation for components and their connections. The middle layer, it executes changes in the underlying layer based on status reports it gets from the underlying layer. And to that end, it uses plans. Now, if it has no plan available to deal with the status change, it will request the top layer, and the top layer will then look into the goals and say, okay, how can we define new plans to deal with this problem? And these plans are then given to the change management layer that will enact the changes according to that plan in the component control. So you see the three-layer model structures the problem of self-adaptation in two fundamental things, change management and goal management. Now, architecture was also central in the way to reason about self-adaptation, in particular architectural model. And you see here a bit of a complicated figure, but in fact, it's not that complicated. At the bottom, you see a service-based system, a server system, client service system. And the idea would be to keep the response time below predefined maximum, independent of the changes in traffic and bandwidth conditions and so on. Now, the model manager, you see there 4 components, model manager, constraint evaluator, and so on. They form basically the feedback loop. This model manager, it will track all kinds of data from the system and updates then models at the top, like the properties, for instance, of the different, for the different clients, the response time, the bandwidth that is used by a group, and so on. And then the constraint evaluator has rules that it periodically checks. And if a violation is detected, it will trigger the adaptation engine, and the adaptation engine then will decide what strategy to apply. For instance, if the load of the group is too high, I might add a server to that group. Or if the bandwidth for a particular client is too high or too low, sorry, too low in this case, then move the client to a group with better bandwidth conditions. And at the end, the adaptation executor will then execute these actions and perform the changes of the strategy. So the key fundamental insights of wave 2 are, there are 2 basic concerns, change management and goal management. And any engineering of a self-adaptive system should take these 2 concerns into consideration as first-class citizens. Next to that, an architectural model allows you to reason about the system. And as we have seen, it allows you to reason about the system in a global way, the system-wide perspective, and reason about constraints at system level, properties at system level, and the like. This brings us to wave 3, which is called runtime models, or sometimes also called models at runtime. The focus of this wave is a bit later, from 2009, the main focus to 2014. And in fact, this wave was triggered by the need for, although we have now coarse-grained architectural ideas, what we see in practice is that if you want to realize self-adaptive systems, it remains very complex. And there are too many complicated details that need to be tackled. And the idea of this wave was to apply the ideas of model-driven engineering, which was at the top of interest at the time. We plan to extend that to the runtime, not only at design time, development time, but also to the runtime. And actually what came out of this wave was that we need not just one architectural model, but we need to have distinct models, runtime models, that support the runtime decision-making of a self-adaptive system. Now, a lot of text, I'm sorry, but it is necessary to define 2 key properties here. On the one hand, a runtime model is a first-class runtime abstraction. So it's something that is represented at runtime, which might also exist already at design time, but then kept alive at runtime. Now that model represents anything of the system that is relevant for the purpose of realizing self-adaptation. Now, a runtime abstraction of a system or a part of it needs to be consistent with what's going on in the world, either in the system or the environment. And sometimes initially they want to say, okay, these runtime models need to be causally connected with what they represent. But we learned over time that strong causal connection is in fact not possible. And we need to allow some discrepancy between the state of the system and the model. Of course, in such a way that it will not invalidate the decision. So there might be some, let's say, some noise on the status. There might be a slow delay, but not such that the decision making would be negatively affected. Now, if we apply runtime models, there are different strategies that have developed over time. You see the three main strategies here sketched in these figures. And in fact, number A here, MAPE components share K models. That is what we already have seen, for instance, in the server example that I gave before. So components of the MAPE loop share models. Another way, very interesting way, is that the MAPE components, they exchange models. So the models are not accessed altogether by the different models, but they exchange the models from one to another. And the last, more exotic way is where not only the runtime models are models, but also the MAPE elements are models. And then these MAPE models, of course, they need to be executed by some execution engine. Now, for the sake of time, and we'll only look at this second example, MAPE components that exchange K models. And here you see an example where it happens. You see at the bottom, the managed system that is instrumented, in this case, some business application with probes and effectors. And at the top, you see this online model space, as the authors of this paper called it. That's a managing system that reasons over the models. And in between, you see this causal connection to realize this weak causal connection. Now let's look at these models to explain a bit what's going on here. The causal connection, the event processor, it collects data from the environment, and all this data is put together, all the relevant data, of course, in what is called a context model. And then the goal-based reasoner, it has a feature model that represents the variability of the system, and a reasoning model that associates features with particular context. And then what the goal-based reasoner in the middle does, it derives a feature model for the current context. So it looks at what are the variability, it looks at what is the current context, and then derive what kind of features do I want to have for the moment. For instance, there is bad bandwidth, okay, I need to reduce the resolution of my GUI, for instance. And based on that, the model weaver will then compose an architecture for the system, and then first check that composition, whether it's valid, and if it is valid, it will give that model to the configuration manager that will enact it into the application. So all in all, what you see here is these four elements, goal-based reasoner, model weaver, event processor, and configuration manager, are basically realizing again this feedback loop. And what you see is that they exchange models with one another to realize self-adaptation. So the third way of learning is that runtime models allows us to manage the complexity of self-adaptation. In fact, I wrote here design, but also the reasoning of adaptation at runtime. And what we do in self-adaptation is we use a notion of weak causal connection, which at the moment is not formally defined, but the intuition is there. And we saw three strategies to use runtime models. They are complementary, they have advantages and disadvantages, and the problem at hand, you have to decide which one to take. This brings us to the fourth wave, requirements-driven adaptation. So requirements-driven adaptation, which run more or less in parallel with models at runtime. Here the problem shifted to the requirements of feedback loops. Actually, before this wave, people were not considered the requirements problem as such an important problem. They're looking at feedback loops, but without asking themselves, and what is actually the requirement that allows us, that is underlying the need for that particular design of the feedback loops. So the topic went then of this wave was moving to requirements-driven adaptation, central, requirements at the center of the attention. And what we came out of this were languages and formalisms to specify requirements and use that in fact to operationalize self-adaptation at runtime. So I look at two mechanisms. The first one is very famous. One is relaxing requirements. Here you see a small part of a goal model of our IoT system. And in the middle, you see maintain packet loss threshold, which is of course affected by the decreasing signal noise ratio, which comes from network interference. So maintain packet loss threshold is not always easy. And what we might do is we might say, okay, let's relax that. We cannot in each cycle have the packet loss threshold, but on average, we might keep it over 12 hours. And that way we can mitigate this decreasing signal to noise ratio. Now, of course, just stating that, that you need it over 12 hours will not be done automatically. You need to realize that. For that, we can add another goal, a sub-goal that says, okay, let's keep the signal noise ratio, let's keep it that, in fact, it's smaller than 0, it should be higher than 0. The signal should be higher than noise, so 0 is the minimum. Sorry for the typo. Now, also keeping the signal to noise ratio above 0 is not something automatically. You need to operationalize that. So in that we define a requirement that we achieve the proper power setting at all time. And that then is done by this managing system for the IoT, the feedback loop on top of it. So this way we can in fact relax our requirement for packet loss over a period of time, which allows us temporarily to violate, but on average over 12 hours not to violate it. And for that we need this extra managing system. Another, in fact, basically similar thing, but another type of viewpoint are so-called meta requirements. And here you see another type of goal model for the same system. The goal is to transmit data, and we can do that by transmitting packages over the network. And if we transmit packages, of course, it is the two soft goals related to that are reliability and energy efficiency. And here the quality goal again might be initially keep the packet loss below 10% and minimize the energy consumption. Now, as we saw before, keeping the packet loss below 10% in each cycle might be difficult. So we can say, okay, we add an additional meta requirement, so-called awareness requirement. And that awareness requirement say, okay, this quality requirement should be achieved with 100%, but not in each cycle, but over a period of 12 hours. And that way we also get, in fact, a relaxation of the requirement. Again, this requirement will not automatically be achieved, but need to be realized. And for that, we need some control variable. And in this case, what we will do is we will change the network settings, meaning we will change the power setting of the modes. We will change the paths that modes are communicating data, as we saw in the beginning of the presentation. So the key insights of wave 4 are requirements is something that we cannot achieve maybe all the times due to uncertainties, and we can have techniques to deal with that, such as relaxing requirements and meta requirements. A point I didn't mention before here is that these are requirements about the quality properties, but of course a feedback loop needs to behave correctly, but that's also something that has been studied in wave 4. Let's then go to wave 5. Wave 5 is about guarantees under uncertainty, which is still an active area for the moment. So in fact, around 2010, people get the insight that uncertainty, we talked about it all the time, but we didn't handle it systematically. So we start focusing at it and how to mitigate it. And the particular focus was on using formal techniques at runtime. So now uncertainty, what does it mean? Here you see a kind of working definition. It's a deviation of any type of deviation of deterministic knowledge. And this deviation might lead to a reduction of confidence in what you decide about how to adapt. And in fact, uncertainty in self-adaptations can be anywhere. In the context of the system, the environment, in its goals, even in the system itself, if it is a large-scale system. And of course, humans that are somehow involved in the loop, either as users or as operators or whatever. Let's look at two particular things that are important when we want to tame uncertainty, meaning we want to get assurances that the uncertainties are tackled properly. First, the analysis of the adaptation options, and then the selection of the best option of all these options. So here you see a model where we have only focusing on the analyzer, and the analyzer can at any time read models that have been updated by the monitor. You read the models, and then it might say, okay, let's now configure a set of quality models that are important for my adaptation goals. Let's configure them for a particular configuration I. And then the analyzer tells the model verifier, invoke now a query in this quality models for quality property G for configuration I. And then the model verifier will use the quality models and perform a verification. And then it will write the results. In fact, the middle box here, the QIG will then be written to the verification results. And then the analyzer repeats this for other configurations and other quality properties. And at the end, the full table of the verification results will be available. And then the planner can say, okay, let me read the verification results and my goals. And then it can say, okay, which one of these, all these results are the best? Which option is the best one? So it does, for instance, this utility computation as I showed you before, and it selects one. Then it reads what is the current situation of my system, and based on what I need, the configuration, the option that I selected, and the system configuration I have now, I generate a plan to adapt the system. And then I write that plan to the knowledge, and there the executor can find the plan to execute that plan. Let's look at an example where this is applied here. You see a service-based system where multiple service instances can be used to perform some service for users. And the operational model here could, for instance, be a kind of Markov type model where the transition between different states, where different services are invoked, represents, where the circles represent different states that corresponds with services that need to be invoked. And the numbers on the arrows represent the probabilities that particular transitions are taken. So for instance, there is a transition from 7 to 14. 14 state is a failed analysis. 7 is doing some analysis. And the probability for them is 1 minus C, while the probability to succeed is C. And this C is a parameter that changes, of course, over time. Services might fail depending on the type of service you use or other properties in the system. And now we can define properties of the system in a formal way, such as you see here. The probability that eventually the service will fail should be lower than equal to 0.40. And then the analyzer can use the model checker to check for all different configurations. What is the expected probability? For instance, for configuration 2, the expected probability is around 0.10. And the service failure will be around 0.1. So it can do that for all different configurations. You see here the threshold goal is this 0.14 that I showed you at the top. And at the end, the planner can take all these computations of the utility and then see which of the selected service instances that have been analyzed should I pick. And the one with the highest utility is then selected for adapting. And that change is then applied by the executor. So wave 5 learned us that uncertainty is a key issue in self-adaptation, and that in order to attain that, we need to ensure that we provide guarantees for the compliance. Now note that in self-adaptation, we reason over models at runtime, and of course any guarantee we give are guarantees for the models, and we need to validate the system to ensure that our guarantees are also actually applied by the system. This brings us to wave 6, where the focus shifted to so-called control-based adaptation. Now, wave 6 was really established at ICSE paper in 2014, where control-based adaptation was applied and presented the first time. In particular, a particular type of control-based adaptation. Actually, control has been used for adapting resources for a long time. Think, for instance, on the work in the ICA community for many years. But here the focus shifted drastically. So the focus, in fact, the argumentation was that control provides a mathematical basis. So that gives you guarantees, in fact, by principle, which, as you saw in the previous wave, was a hard thing to get. If you need to do runtime verification at runtime, it's a hard thing to establish. So if you get it for free from control theory, that would, of course, be a big benefit. So people start studying how to use control theory. Now the focus mainly is on the design and the analysis of the feedback loop systems. And in particular, the difference here in terms of this wave is that researchers were looking at automatic construction of feedback loop systems. This has to do with the fact that control theory is a complex area, and software engineers are not always the people that are familiar with the underlying mathematics. So people want to construct automatic feedback loops. derive them automatically. I will show you now the basic principle that has been applied for this automatic construction. You see here the setup of the different phases, how to construct and operate a control system. And I will go over it one by one. So in the state, if the switch S is in state switch S in state 1, then the target system is, the model of the target system is built. So basically what we do is we feed the target systems with input values, control input here at the bottom of this graph. We give it values from a minimum to a maximum, and we measure what is the outcome. Yeah? And this outcome we plot at the system output Y. And then at the end, when all the data points are tracked, then we do some regression and we find a model, a linear model for the system. And for many systems, we can find such a linear model. Then we switch to S to state 2, and then basically we configure the controller. The controller just is in fact a mathematical expression that says what is the control output in function of the previous control output minus a product of, on the one hand, the error that you see. The error means what is the output of the system compared to the reference input that I need, and the reference input is my goal, and the control error is then used to compute the new control input for the target system. And the P is a value that is called a pole. It's a parameter that we can set that determines basically the behavior of the controller. Sorry. And the alpha is the slope of the curve of the model of the system that we have determined in the previous step. So, and now the controller can be enacted. And if the controller is enacted in stage 3, you see the controller is just changing the control system based on the differences it measured between the output and the reference input, and the controller then adapts the target system accordingly. And what we know from control theory is that this kind of configuration provides you all kinds of guarantees. For instance, you see that if the goal changes at some point, the transition from the system towards that goal will follow a particular path where we can say something about the overshoot that happens. We can say how far will the output diverge from the control, from the goal once you have the steady state in terms of steady state error. We can say how long will it take, the settling time until we reach that state, and so on and so forth. Now, as we have used a singular linear model of our system, that's of course a bit naive. The system might, under different conditions, behave slightly different. So what we do is we equip the controller with a Kalman filter that tracks the changes. So, and the slope of the model of the system will periodically track, and if you see that something needs to be changed, the Kalman filter will identify the new slope, and the controller value alpha will accordingly be adapted. And that way, we in fact have at any time a linear model, but a linear model is fluctuating based on changing conditions. And in fact, many applications have shown that this works very well. Here you see a concrete realization. I will not go into details here because it would take me too long. But you see here the input takes many set point goals. There is one optimization goal. Controllers take care for set point goals. And a simplex optimization module will then use all the control signals and the optimization goal to identify the actuation signal that it needs to achieve, to enact on the target system to bring the system or realize all the goals. So this wave learned us that control schemes indeed work for self-adaptive systems and that we can automatically construct them. And linear models, in fact, have shown to work pretty well. Does not mean everything will be solved, but we have a bunch of problem domains that have shown good results. And here we get control guarantees. Basically, we can formally identify these with lightweight effort. However, here again, these control guarantees are at the level of the model, and also, just as in any other system, need to be complemented with validation. Let me now go to the last wave, learn from experience, which is a very recent wave. In fact, there were also some precedents, some early work in this area. One of the works is the fusion work of Sam, who introduced me here today in the talk, who already used learning many years before. But the main focus started in 2016 where you see that the problems that people were working on, they grew in scale, and also the levels of complexity were complicated, and people start to look into learning techniques to solve that. Now, this is a very early stage wave, in fact, but we have already nice results. Among them are Bayesian estimator. This was a paper also at ICSE presented by the group of Carlo Ghezzi years ago, where we keep, in fact, runtime models up to date using Bayesian estimators. Another work recently published was deep learning that reduces large adaptation spaces. And another interesting work is Q-learning to improve autoscaling. But I have not so much time, so I will use one more understandable example. Here you see again this adaptation space of our IoT system. And as you see, many options. And here on the right-hand side, you see how one property, latency, fluctuates. So if you if this would represent a yellow dot here, the yellow dot will bump up and down all the time. And of course, all packet loss will change. So it will go left and right and left and right. So this yellow, the current configuration, will jump into the box, out of the box, into the box, up, down, and so on and so forth. So a complicated problem. So what people did here in this research is they defined a deep neural network with a set of core layers that are shared among all the goals. And then they add specific heads for each of the goals. So in one move, you have, for all goals, you have results, and that go to reduction stages, and then you get a reduced adaptation space. Here you see an example. You start with the gray, symbolic, the gray configuration space. And then in stage one, you take, in fact, the intersection of all threshold and set point goals that are valid, meaning all the options that respect the threshold goals, or all options that respect set point goals within a certain epsilon window. And once that is done, you can use the results of the optimization and rank them according to some quality property. And that can then be used to verify the adaptation options. And instead of verifying all the options, you just need to verify the reduced space. And then you need to integrate this, of course, in your MAPE loop. And you see here in our case that the analyzer and the planner are those entities that deal with, that exploit the deep neural network and do the reduction. And here you see some results from a particular point in time. So all the dots, the learner has predicted all the orange dots here, of what is it, a brown dots at some point, and it does a pretty good job. A little bit later, you see the whole space has to move to the left, but still the learner is able to keep good track of the changing conditions. So this learning wave learned us that machine learning can deal with all kinds of problems. For all kinds of functions in the feedback loop can be supported. Now, as I said, learning is now a very popular topic at the last themes. Several papers were presented on learning, solving new and complicated problems. So we are enthusiastic about it to see what it will bring for the future. So to conclude this talk, I will briefly talk about a few other things. First, I will say a word about the maturity of the field, and then I will look at some interesting problems that are still open for research in our area. So I did some analysis a few years ago on the maturity of the field. I used this red wine and riddle model that was presented in the 80s at ICSE. And what you can see is that this field is now in the stage of internal and external enhancement and exploration. This means that we are applying our problems to, let's say, controlled settings that are relevant for practice. And you see that in the presentations at conferences, in journals, you see people more and more start to getting more realistic applications. By the way, that does not mean that these things are not used in practice. I showed you examples in the beginning of the presentation about industrial applications. But as I said at that time already, the focus is particularly on managing resources. And of course, if we want to really exploit the possibilities of self-adaptation, we should also look at higher levels of the technology stack, basically the software stack, so at application level. And for that, we need, of course, some widespread application in practice. If we are not managing to do that, self-adaptation will somehow end up in a niche. So let me look now at a few challenging problems that we face. I pick here a number of interest. So within current waves, there are a number of important problems that have that still require research. One of them is decentralized settings. So this is something that we know for a while already. First papers were already written probably like 8 years ago, I don't know exactly, but at that time people were already mentioning decentralization. We need, MAPE is basically conceptually a centralized concept, and the feedback loop is a centralized concept, but in practice one single feedback loop might not always be feasible. When I work on these IoT applications and we think about smart city settings as we have now, we have rolled out a whole IoT system at the Leuven area, then a single feedback loop collecting all the data in a single feedback loop is out of the question. So you need then, if you want global properties, you have multiple feedback loops that need to coordinate with one another. But how to do that in a systematic way is still a very open challenge. Another problem is the uncertainties. And you have seen different examples here in this talk where uncertainties are typically associated with parameters in models, where we say, okay, the probability that this transition will take is X, the probability that that transition will be taken is 1 minus X. But of course, this is not the only, this is not the only type of uncertainty. Much more complex types of uncertainties might occur. For instance, we might not have really a good idea about the structure of a system. I think again about these smart city systems where you have a big, huge networks. I might have just a good idea about my local structure, but have only less good idea about maybe neighboring parts of the network, and far away regions one might have only a vague idea about what type of structure there will be. Now we have currently no solutions to deal with this kind of uncertainty, so there is research required on that. And another very interesting technique that has been studied already a few times, and now the last themes we saw again examples, is exploiting search-based techniques, because for certain problems, search-based techniques are really very efficient in terms of finding solutions, finding things out of big data, which might for machine learning not always be feasible or easy to do. So they are complementary techniques, and they offer definitely interesting opportunities for dealing with complex types of problems, in particular those with huge amounts of data. We can also go beyond the current ways, which is obviously some kind of speculation. But one of the really interesting things that has been coming into the picture recently is handling unanticipated change. So for now, in all the examples I showed you here today, we basically anticipate somehow the change. We know somehow boundaries on what we can expect. We don't know exactly when it will happen, the degree that it will be happen, but there is some knowledge about certain things. We have boundaries on what we might expect. So the question then is, can we deal with something that we have not so much information about, something that we have not fully anticipated? And that opens, of course, a fascinating area where you can then deal with things you have never anticipated before, and things that might happen. There are example movies on YouTube where you see a Tesla car coming, or a car driving in front on a road, and suddenly something completely unexpected happened. A tsunami is moving. There is one of these nice movies, is coming in front of you, and then the driver quickly turns around. So you never anticipated that when you build a car. You never anticipated that problem even as a human being, but you're able to deal with that. Can we build software that can handle these kind of things? Is a fascinating question. Another interesting area for research, which is already somehow also starting, but is crucial for practice, is the level of trust that we can have in these systems. Now, if we automate, this is something that we know from history. If humans automate something, in the beginning, people are not trusting it. The first people that were flying with an airplane were not trusting that thing so much. So it's by showing validity of the things we build that we get trust. Nevertheless, it does not mean that we cannot study how to establish trust and how to ensure trust. What is the problem of trust? It's very closely related to humans, probably humans in the loop. I saw that in my own work when this IoT area, companies that we work with Trust is the key issue. They said, okay, maybe human is not that fast when it is need to respond to some problem, but on the other hand, whenever something happens that you never thought about, the human will see it and it will take action. If you leave it to a system, will that system see it? Will it take action or not? Maybe it ends up in a disaster. So you see this tension between trust and having humans in the loop. And the last topic, it was also subject of debate now at the last Teams conference, is ethics in self-adaptive systems. Now, self-adaptive systems share properties of autonomy. A system take action on behalf of humans, and then obviously all kinds of issues emerge, such as, for instance, is my system taking actions that are not making any difference between groups of people, for instance? Am I not violating any legal requirements and the like? So there is stuff to do here, and that should probably be go in tandem with ethics in autonomous systems. Self-adaptation share these properties and need to go in tandem with them. But there might be differences in terms of how to implement technically the properties that are required to ensure ethical principles when we talk about self-adaptive systems. So in conclusion, you have seen self-adaptation has to do with automation and handling uncertainty. And I believe that the systems, and I'm not the only one, that we see today and that we will see in the future will need more of this. And there will be we need more of automation. We need more of dealing with complex uncertainties. So self-adaptation aims to contribute under these conditions to high quality software. But we are not at the end of the road here. On the contrary, we just in fact basically started the road. So what we need to do now is there is a need for consolidating the knowledge and propagate this knowledge into the field. We are actually, for the moment, setting up a big study where we are in Europe at many different countries, where we investigate how people apply these principles of self-adaptation in their current practice, because people might just don't know that this is self-adaptation, what they do. People instrument software, a lot of software with all kinds of features to track systems, their behavior, and even take action based on what they observe, sometimes automatically, sometimes semi-automatically, sometimes just by humans. But there is a lot of going on here, and we would like to understand better what is the actual state of practice. And of course, if we propagate technology in practice, this will not meaning that there will be no research problems. There will be new problems will emerge, and we need to tackle these new problems. Okay, let me conclude with thanking my colleagues here. I list here my PhD students and my main colleagues that I work with at KU Leuven, also Linnaeus University in Sweden. And on the left-hand side, you see the cover of a book that I just finished that will be published by Wiley, and that will be available very soon for anyone who wants to know more about self-adaptive systems. And actually the talk today are some excerpts that I took from this book to present you. That brings me to the end. Thank you very much for your attention.
Thank you, Danny. So I'll clap on behalf of everyone.
Thank you.
This was very informative talk, and you did a great job of summarizing a lot that has happened in this area. So I have a few questions, but I do want to let the participants know that they can ask questions. Either you can put it in the chat here, or you can use the Q&A feature in Zoom. And so since I know people might be thinking about questions, I guess I'll start, and then we'll see if the attendees have any other questions. So Danny, so you talked about these, I think, 7 waves. You talk about 7 waves of self-adaptation. To what extent do you see these waves as being overlapping versus being complementary to each other? In the sense that, to me, it seems like some of them are complementary, meaning that they complete each other, while others are, you choose this approach versus that approach. What are your thoughts about that? Have you thought about to what extent they are actually trying to combine to solve the engineering of these systems, address the challenges of engineering these systems, versus there are just alternative theories of how you should go about designing these systems?
Thank you for the question. This is of course, yeah, it's a fascinating question. It is, let's say, it's a perspective. Actually, the 7 waves is my own perspective. So maybe if someone else would look at the field and try to identify how research and engineering has evolved over time, they might have another outcome. I just try to, you know, one of the big questions when I was doing this effort was trying to understand how the different strands of research have, how they are somehow connected with one another. I didn't highlight so much here today how these waves are connected with one another, but in the book there, you will see that all these waves have been triggered by other waves. So I'm not saying that this is disjunct. It would, of course, not. These things are all putting together. I mean, they make a whole, and there is not something like in that area we do specifically this, and in that area we do specifically that. Take, for instance, architecture-based adaptation. One of the key insight there is an architectural model is a very good level of abstraction to reason about adaptation of a global system-wide. So it provides you the lighter level of granularity and to reason about the software system and its properties or constraints. And then the next wave is the models at runtime. Now in models at runtime, we also talk about runtime models. But the insight there is architectural models, the focus in architectural model was usually on the architecture of the system, its components and connectors. And it was annotated with properties and so on. While then models at runtime said, yeah, but hold guys, if you start to annotate these models with this and with that and with that, at the end it is a cluttered thing. You don't understand really anymore what you're doing. So we need distinct first-class models, one for the system, one for the context, one for the quality properties, and so on. And then if you even go further in uncertainties, handling uncertainties and guarantees, people say you need quality models and you need uncertainty first class represented that allows you to reason about. So you see, runtime models is something that is over different waves spread. But there was one wave where you really got the highlight of these runtime models as a topic of research. What type of runtime models do we have? What type of use cases can we identify? But of course, runtime models are used anywhere and also in other ways. So you see, I'm just saying like it is a kind of trying to understand from different angles the field, but without any claim that this is the one and only way to look at the field. It's just one way. And
okay, this is, I mean, to me, it was fascinating the way from your perspective, these are the 7 waves, and I thought it was interesting because I guess one thing that was surprising for me was that decentralization was not a wave, but it was kind of like a sub wave across all of these 7 waves, the way you had structured it.
Yeah, look, decentralization is a complex problem, and yeah, it has been studied already. There is already research on that, and it is actually something that has the last 10 years been repeatedly studied again and again. But what I want to say at the end, when I said in Outlook that decentralization is still a kind of open research problem, what I mean is there is still, I just basically got myself to research projects accepted recently about decentralization of self-adaptation. And what I made there as claim is that, look, there is interesting work has been done, but how to engineer this in a systematic way in a self-adaptive system is not really well understood yet. There is research required to get a better grip on it, I would say.
All right, let me see. So if there are any questions, you can put them in the chat or put in the Q&A. In the meanwhile, I have a couple other questions for Danny. So Danny talked about these learning techniques. Sort of, I think learning-based approaches was a 7th wave in what you were talking about, and you talked about deep learning techniques. So the challenge that I see there is that with a lot of these techniques, learning-based techniques, you need a lot of data. right? You need a lot of training data, especially with deep learning techniques. What are your thoughts about that? I mean, you've done some project there. How did you, like that chart that, for example, you showed us, where did you collect that data? Like, do you generally think this is an approach that can be applied to a lot of systems, especially when you're engineering a system and you don't really have that data, for example?
Yeah, of course, if you need data to apply a learning technique, you will need the data, otherwise you cannot apply it. But in our case, this IoT system, it depends also on the stakeholder. If you work with someone and you need data, then it depends on how much effort is required and what is the effort worth for the stakeholder to collect that data. In our case, for instance, we built a simulator of the real network. And what we then did is we collected data from the real network. So we deployed the real network. We collected data, for instance, of the interference along links. Just as an example, or the traffic generated by modes. We collected that data and then we fed that data into our simulator, and then we could simulate that system for a period of a day or a week or whatever we needed to have the data that was representative.
Mm-hmm.
And of course you can validate it. You can check down whether if you apply your learner and you use that on the real network, will it really actually work the way it should work? And in our case, we could confirm that the data we collected was good enough to use this deep learner. In fact, it worked very well. It helped us a lot to, in terms of reducing the time for adaptation that we needed. But yeah, in general, if you cannot collect the data and you need data, the thing is that the tool is not applicable then. So it can be in certain domains complicated. The IoT system, it was relatively simple because we had a controlled setting. The company built a network in our campus area, in fact, 2 networks. And we built a good simulator, and we know by now that the simulator is representing the network pretty well. Mainly, I think, because we use all kind of parameter data that is coming from the real network, which helps, of course, a lot to make a realistic simulator. And once you have a good simulator, of course, you can generate data as much as you want.
Mm-hmm. Mm-hmm. So in the experiment that you did, the simulation was relatively accurate with respect to the actual behavior of the system.
Indeed, yeah. Mm-hmm. We know that from the past because we did experiments exactly to compare. Is the simulator, what is the result of the simulator? What is the result of the network? And we compared. In fact, when we built the simulator, we used that to tweak our simulator to get it right.
Mm-hmm. Mm-hmm. The system that you guys built, did you experiment with, as the system is making decisions, do you try to incorporate that? So a kind of a runtime learning as well, or was it just kind of offline learning and then?
No. The learning that I used here, this deep learning network, it starts with, first you configure the network, then you deploy the deep learner model, you deploy it, and then you train it a few cycles. In fact, it learns, the instant initialization goes very fast. We learned that it is very easy to initialize. Which also indicates the type of problem we have. Might not be the most complicated problem for this deep learner, because if you can train it so fast, it also tells you something about the complexity of the problem. But nevertheless, it's then the complexity of the problem for the deep learner to learn, I mean. But then we use the deep learner at runtime. So the learner predicts what is the set of configurations I need to verify to make my decisions. And then you verify these options and you feed that data back into the learner to continue the online learning. So in that way, of course, if you would not do that, it will degrade after a while, because the system might go from one uncertainty area into another uncertainty area. And if you have not prepared your system to deal with new areas in the uncertainty space, yeah, of course, your learner probably will learn only very slowly or not learn ever. So we need to feed the results that we have into the learner to continue the learning process. Actually, what we do, instead of, we not only verify the adaptation options that are suggested by the learner to verify, we also take a random sample from the remaining adaptation options, just to keep exploring the space all the time, as you always have in learning. the exploitation versus exploration tension, in fact.
Very interesting. So we have a question from the attendee, Kun Leo. He asks, it seems to me that self-adaptation is used widely in constructing software. And I'm wondering, what is the role of self-adaptation in the multi-agent system? Is there any specific research questions about self-adaptation in multi-agent system?
Yeah, that's a very interesting question as well. Actually, I did my research, my PhD research on multi-agent systems. So I have some, let's say, some background knowledge about the area. There has been not so much research on self-adaptation in multi-agent systems. I hope that the beginning of my talk, where I explained these principles, made clear that a multi-agent system and a self-adaptive system is definitely not the same. A multi-agent system is a system that has also, if you want, a feedback loop, but that feedback loop acts in an environment. So the agent observes the environment, reasons about the knowledge it collects, and then take decisions in the environment. Now you can make a multi-agent system, or let's say an agent system to start with, you can make that a self-adaptive agent system if you put a feedback loop on top of that agent. And that you say, okay, let me observe how that agent is making decisions based on the results it gets from his decisions. And then you might say, okay, I adapt my agent decision-making over time for whatever reasons, to keep it performant, to ensure that it doesn't result in errors, because I observe that sometimes it might result in errors under certain conditions and the like. So I think one of the challenging things there is that in this area, applying self-adaptation might be non-trivial, because since a multi-agent system, even a single agent system, an agent is a reasoning engine. And if your adaptation layer, your managing system, has to reason about another reasoning layer, it might not be easy for how to model that, what do you need to capture? What is the essential information you need to capture to reason about how the agent makes decisions? What context data do I need to understand how to adapt the reasoning mechanism to make that system, let's say, qualitatively better? So that's a challenge I see. Let alone if you talk about a multi-agent system, then inherently this decentralization comes into place. So if you have a self-adapting agent and you have another self-adapting agent, it might be necessary that these two managing systems need to coordinate with one another to adapt the underlying decision makings of their agents to keep a kind of consistent, to ensure a consistent solution system-wide then. So I think it's a very fascinating area. It's a very fascinating area for the future, definitely, but a very challenging area. Mm-hmm. I hope that clarifies a bit my answer here.
If there are other questions, you can put it in the chat box here. We still have some time. And I guess one question I'll ask Danny, kind of following up on Kun Liu's question here. I guess his comment, he's saying self-adaptation is used widely in constructing software. I guess let me play a little bit of devil's advocate. From my experience in this area, a lot of techniques in the community that we have been developing haven't been really adopted by industry, and that seems to me partly because building software in general is complex, and people really like to have predictable systems where they can test them and so on. And and it seems to me maybe one of the reasons these techniques are not being adopted is because they're just difficult to have assurances and have guarantees about the system behavior. And without those assurances and being able to properly test the system, people generally have reservations about deploying these techniques. What are your thoughts about that?
Yeah, look, I think that is definitely correct. Your observation is correct. I would not say that this has not been much used so much. Actually, our study isn't exactly that I was referring to during the talk, is exactly to understand to what extent have people yet be inspired by, or do they do, even independently of any research that has been done. We would really like to understand to what extent do people build feedback loops on top of software to deal with quality properties of software? I would like to understand that better. So at the moment, my argument would be, we really don't know so well. We know that self-adaptation has been used a lot in particular areas. In elasticity in the cloud, people are using it, tools exist, they are used while we speak here. And it is a very typical example of a self-adaptive technique. Mm-hmm. So there are solutions in the field used in practice. Now, if we talk about application software, we really don't have a good idea about it. And you might say, and actually I confirm that trust in self-adaptation is a key issue, but at the same time, we use machine learning in a lot of areas. We also have no idea about how can we trust these things, but we are equipping our autonomous cars with machine learning, and we plan to do that probably even before we have full assurances it will happen. So I would say, yeah, at some point, evidence comes from practice. Evidence comes from, of course, you cannot deploy something that is untrustworthy in a critical situation, and we will not do that. We will not be allowed. And if you do that, you will end up in jail and stop your practice. But at the end of the day, we are working on assurances, but practice is important. We need to apply this gradually into more and more applications. But before doing that, I really want to understand what is the state of practice for the moment. Mm-hmm. So that's why it is important that we now reflect a bit on it. We have, as a community in the self-adaptation world, spent 20 years of defining all kinds of fancy solutions. We see some practical applications, but now I would like to understand what is the state of practice, to see how can we consolidate our knowledge. Maybe certain people can just gain and benefit from more systematic engineering practice just by understanding a bit of the outcome of research and say, wow, that could be interesting, or this kind of requirements modeling technique could be interesting for us. And maybe you're not aware, maybe they do it in an ad hoc fashion. Mm-hmm. So I think there is room for transferring the knowledge that academics have defined into the practice. Mm-hmm. But it is a kind of, working in two directions. On the one hand, understanding what's going on the other hand, and transferring that knowledge to probably improve practice or create opportunities. Yeah.
Great, thank you. So we have a question from Ricardo Caldas. He's asking, thanks for the insightful presentation, Danny. I'm curious, with the IoT simulation that you mentioned during the presentation, how did you encode uncertainties in your simulator, and to what extent they conform to the uncertainties faced in the real world system?
Yeah, that's a good question. That is how we encode the uncertainties. In our case, there were two important types of uncertainties. One type of uncertainty was, when do modes generate data? Because these modes are battery powered and don't send data if there is no data to send. They just keep sleeping because it costs energy to send a void message, and they won't want to spend that energy. So what we did is we tracked this. We tracked in the environment how much data these modes sent over time during a day. And we collect that, and then we generated patterns from that data that we collected. And then in the simulator, when a modes sent data, we just use this collected data to generate the data in the simulator. Another thing was the interference along links, which might come from all kinds of sources. It might come from the weather. It might come from people that walking there, other networks that interfere, cars that drive in the neighborhood, you name it. So they're the same. We collected the interference along the links in the network. And there again, we defined patterns of how the interference behaves basically along the links. And then again, in our simulator, we have parameters in our model that represents these uncertainties, and we use the patterns from the real system into the simulator to simulate the behavior of the world, let's say, in the simulator. Then.
Danny, was this a off-the-shelf simulator, or is this a simulator that you guys built yourself?
No, we built it ourselves. Yeah, we started actually with another simulator, but at the end of the day, we decided to build from scratch to, yeah, it is tweaked towards this particular domain. it is not like a particular instance, it's a simulator tweaked to this type of problems where you have battery powered modes that operate over an ad hoc network, that are subject to a wireless network, subject to interference. So, and we have two different settings, one over the campus area, as I showed in the talk, and we have another one in a building, where we have now in our building, where I, not so much anymore for the moment, but we have 5 floors and there are modes scattered all over the floors. And they also form one IoT network with one gateway. And we have used a simulator for that network and it worked really good as well. But it's dedicated to these types of networks.
Thank you. All right. Well, we are. I think we're pretty much at the end of the time allotted for this. I want to thank Danny one more time for giving a very insightful and interesting presentation on self-adaptive systems. This was the first technical briefing that has been offered virtually in ICSE's history. And I also want to thank the attendees for coming to the technical briefing. We have 4 more technical briefings. You can find them on the ICSE program. And I'm in Pacific time, so I'm going to say good night to everyone. I think Danny's in Europe, so good afternoon, I guess, or good morning. And this concludes the today's presentation. Thank you.
Thank you, Sam. Bye-bye.
Thank you, Danny.